presentation today on Desargues' theorem. So what initially interested me in this is last semester I took a class taught by Lee Atkinson called History of Math by a Thread, where I first found out about projective spaces, which are very, very interesting to me, but are not something that we cover in the undergraduate courses, at least to my knowledge. And so a fundamental part of projective spaces is this idea of perspective. And so Desargues' theorem is almost completely based on perspective, so we will not be getting into projective spaces, but a perspective of a perspective is a projection. So we're on our way towards projections, excuse me. So in art, there became this focus with accurate perspective around the 1400s, and it was first perfected by, I can't remember his first name, but Alberti, who created this thing called the veil. And so what the veil does is it fixes this person's perspective. As you can see here, this man is not only in one place, but also has something where his eye looks through. And so this is to maintain this single perspective that we're working on. And then this image that he's drawing is shown through a coordinatized grid, which then helps it easier, or makes it easier to be drawn at your hands. So as soon as artists started coming up with this idea, mathematicians were like, hey, you know, there's got to be some way that we can prove some of these things, and just start focusing on perspective. So that sort of led Desargues and a constituent Kepler to sort of think about this point at infinity, or excuse me, before I get this, they started to think about what axiom would change the Euclidean space that we know here into one that accommodates perspective. So I wanted to just go over the Euclidean space axioms. There are 5 of them, and they were originally constructed by Euclid, and so one of them I had to translate because the way that Euclid wrote it was not quite as understandable. So these are basic ones. I'm just going to go through here really fast. You know, 2 points form a straight line. That line can be extended in either direction indefinitely. A circle can be determined given a center as well as a radius, and all right angles are equal. These are all things that we take for granted every time we use a Cartesian plane. And this one's a little funnier, but so given a line and a point not on that line, there is a unique parallel line with which the 2 lines have no point of intersection. And so what this means is that every line that is not parallel has at least one point of intersection. So this is really important for Desargues' theorem, as when you're using Euclidean space, there are a lot of cases that you have to take into account, and you'll sort of see how that works out as we move into his theorem in projective space. So the additional axiom of projective space, or what's called extended Euclidean space, is that parallel lines actually now have a point of intersection. And in a base, so this is a 2-dimensional form of what Kepler and Desargues did, compacting R2. So this is the closest thing we can get to perceiving the projective plane, and there's movement in time, so even though there looks like an overlap here, you'll never actually overlap as you move through this space. So this point at infinity in R1, Kepler and Desargues, the way that they figured it out is that given a line, you choose a point on that line where the origin is going to be. From that construction, you then compact the line, which is essentially to create a point at infinity such that this line becomes a circle with antipodal points at the origin and at infinity. So you'll see how this comes in handy as we actually move into perspective triangles. So Desargues' theorem is, well, actually before I do that, so there were 2 other people that contributed to the idea of perspective shapes. And so before Desargues, so Desargues did his research in the early 1600s. About 1400 years before that, a mathematician known as Pappus came up with a similar idea, but for hexagons. And so it's really cool to think that these same sort of perspective ideas were being taken on 1,400 years beforehand and didn't come to fruition until Gerard Desargues. And interestingly enough, projective geometry was not considered a field until I think Poncelet created a journal that said that it was, and in which that was 200 years later, in which he cites Desargues' work as useful, where at the time of Desargues, with constituents like Descartes and stuff, analytic geometry was the focus, not normal, or not analytic geometry, excuse me. So I want to talk about Desargues' theorem, which states that if two triangles are centrally perspective, or excuse me, two triangles are centrally perspective if and only if they are axially perspective. So I drew these things separately to try and give you an idea of what this means. So here in actually, so these are the titles of their contributions. Pascal's was built on Pappus's theorem, except it is for conics, where Pappus's theorem was based on a broken conic, which actually was just two lines. So Pascal expanded it to a much more interesting place where all conics can determine these crazy hexagons. So here's part of Desargues' theorem. And so when two triangles are axially perspective, you can extend each corresponding side till you can extend both of them until they have a point of intersection right here. And so this is a basic drawing, and you'll see that there are other ones that are less intuitive. So AB and line AB both meet at this point, as do A prime, C prime, and AC, B prime, C prime, and BC. So as it turns out, Desargues figured out that these points of intersection are collinear, as in one line can go through all of them. And the reason that that is has to do with the fact that they're also centrally perspective, which is drawn here. So centrally perspective means that there are three collinear lines that go through, that have a single point of intersection, which will be called the perspective. So this point is known as the center of perspectivity. And as you can see, each line corresponds to a certain vertex. So now to actually get into this, so I'm going to leave this up here, and I'm going to try and write, I might actually, well, so here's what these two look like together. And if I was better at drawing, I could actually draw these two together, but I can't, so here we are. And so when we get to the actual proof of it, it's going to be important to sort of see these things separately, because it might definitively mean that they are centrally and axially perspective, but during the proof it's sort of hard to see that that's true. So keep these things in mind. Alright, so I'm going to attempt doing a proof here. So let's just start here. So suppose that we have four non-coplanar points. And I'm going to actually pretty much go along with this model just to make it better. And I'll tell you any differences that there are. So four non-coplanar points. And so we're going to say O, A, B, C are a member of projective 3 space. So this is in 3 space, which is not that clamshell looking thing that we saw earlier. It's actually where there are lines at infinity all around you that make up this sphere-like thing that are points in infinity. So we have these non-coplanar points, and we also have to suppose that we have 3 points, A prime, B prime, and C prime, such that A prime is a member of the line OA, B prime is a member of the line extended by OB, and C prime is a member of the line extended by O and C. So these two suppositions are assuming that these two triangles are centrally perspective. So, since we know that A prime and B prime are on the line OA, we know that there is a plane. So for notation's sake, I'm going to be using P and then parentheses around points to indicate that it's a plane constructed from these points. So the plane created by O, A, and B. Actually, I should write this down. So both the lines extended by A, AB, and A prime, B prime are both members of the plane extended by the points O, A, and B. Does this all seem good so far? All right. So the same thing can be said for both the lines BC and B prime, C prime for the plane created by O, B, and C. This is true for all three sides. So since both of these lines are on this plane, by the definition of projective space, there has to be an intersection between these two lines. So that even if they are parallel, they still have an intersection. And so we're going to call, I'm going to raise this thing and actually just use.
You can raise it with the button on the wall. Well, acceptable still show that.
No, that's okay. I'd rather show it. All right, so now we're going to have three new points, and they're going to be based on these planes. So we're going to say D is a member of the intersection of lines AB and A prime, B prime. And the same thing goes for these points E and F. And so in terms of this, the points are going to be D, E, and F. And I'm just going to take a moment real fast to write this. Okay, so now we have these 3 points which you don't know anything about besides that the line that they are contained within the that they are the intersection of these two lines. So the cool thing is that now we know something about D in terms of this plane that we have already gained. So we know that this implies that D is a member of the plane determined by O, A, and B. And of course E and F as well. But I can just use this using one example, so I'm not actually going to continue writing all of them down at once. All right, so okay, so now once we have this idea of them being intersections of these two different lines, we're going to focus on a different plane now. And we're going to focus on the two different planes defined by the triangles. So actually, we're going to say that, and this is something that if you have any questions on, I'd be happy to explain, but as a result of D being the intersection of A, B, and A prime, B prime, D is going to be a member of the plane that's determined by A, B, and C, as well as the plane, or I'd say even the intersection of the plane of A prime, B prime, and C prime. And this is true for not just D, but also E and F. So the cool thing now is that we have these intersections of planes. So when planes intersect, they cannot just intersect at a point. They can not intersect at all, or they can intersect at every point, or they can intersect at one line. So in Euclidean space, what we would have to do is we would have to make cases for when they're parallel, but that's why Descartes focused, or at least initially used the projective plane, because it at least made it easier and simple so that even parallel lines have one intersection. So the only possibility is that they have a line of intersection or they are the same plane. And so if in fact there is a line of intersection, this goes back to being axially perspective. So the last thing that I have to do, so this would, since this is true for D, E, and F, this would mean that D, or the line, that there is a line created by D, E, and F that's a part of the intersection of the plane ABC intersect the plane A prime, B prime, and C prime. So this would mean that it's axially perspective, but we don't know that it is a line because we have not shown that they are distinct planes. So the last thing that we have to do is we have to actually make sure that they are distinct planes, and by doing that we're going to go for a proof by contradiction. So the best way that we could do to show that they are distinct is just assume that they're the same. So if in fact the plane determined by ABC is, I think that's the right use of the equal sign, if they are the same, then this implies that A prime is a member of the plane determined by ABC. So if that's true, then there's a line created by A prime that is a member of the plane on ABC, the plane determined by ABC. So now we know that A prime and B, or the line A prime is the same as the line OA. And so by our supposition, since A prime is a member of the plane determined by ABC, so also is the line OA. And so here we have our contradiction as our original supposition based on being centrally perspective is that O, A, B, and C cannot be on the same plane. And so therefore it holds that there is an intersection between these things, and that the line that is that intersection contains both D, E, and F. All right. So that's the end of my presentation. Does anybody have any questions? Cool.